Hello everyone, welcome to this video where I will explain the topic which is called pre-emphasis and de-emphasis. Now what exactly the pre-emphasis and de-emphasis is, where it is used, so all these things we will understand in this video. Okay. Now, as we know in the frequency modulation, the problem actually with the frequency modulation is, even though we say the quality of the transmission is really very good, but we actually face certain problem, especially at the higher modulating frequencies. That is, if the message signal is higher, like say if I take an audio band 20 hertz to 20 kilohertz is the audio band here, at the higher range, maybe some say 5 kilohertz, maybe 10 kilohertz, okay, at the higher audio frequencies, the impact of the noise is actually more on high frequency signal rather than on the low frequency message signals. So to mitigate this problem or to avoid this particular situation, that is to minimize the impact of the noise on the high frequency message signals, we actually use what is called a pre-emphasis, okay, and de-emphasis circuits in the frequency modulation. So this circuit is especially used in the frequency modulation, and also the pre-emphasis circuit is used at the transmitter side and the de-emphasis circuit is used at the receiver side. Now what exactly we have to do in the pre-emphasis and de-emphasis circuits is, okay, now let us discuss that now. So as I told, the effect of the noise is actually more on the high frequency message signals. Okay, so what we have to do is we have to simply increase the amplitude of the high frequency message signals. Okay, before you modulate the signal, okay, and transmission of the signals, you have to pick and choose only the high frequency message signals. Okay, and you increase the amplitude. Okay, so when you increase the amplitude of the message signal, what happens? The deviation actually increases, right? Because the delta deviation is actually given by kf/am. Okay, as the amplitude of the message signal increases, the deviation increases. As the deviation increases, the modulation index or the depth of the modulation also increases, because beta, that is modulation index, or mf, whatever the notation you use, no problem. So beta is nothing but it is delta f by fm. So as the deviation increases, the modulation index also increases. So in this way we can avoid the problem of the noise at the high frequency message signals. Okay, now so what I can define in general the pre-emphasis operation is, okay, it is nothing but it is the artificial increasing the amplitude of the message signal artificially, or boosting the amplitude of the message signals artificially at the transmitter before modulation. Okay, and corresponding or equivalent decrease in the amplitude we are performing at the de-emphasis circuit. Whatever artificially we have increased the amplitude, by equal amount we have to decrease the amplitude at the receiver. So that is done by using the de-emphasis circuit. Okay, so the pre-emphasis is used in the transmitter before modulation, and de-emphasis is used at the receiver after the demodulation process. Okay, and as I mentioned over here, we have to do this operation artificially increasing the amplitude of high frequency signals according to some pre-arranged response curve. Okay, what is that response curve is, I'll show you, because these are all the standards used in America or European countries, which I'll show you in the coming slides. Now, as I told again, why this problem we face, why exactly we need a pre-emphasis and de-emphasis, I'll explain that by referring to these diagrams. That is, this actually represents the PSD, the power spectral density of the noise at the receiver of the FM. So noise PSDs and all, or impact of the noise in the FM, we have discussed that in the last video. If you are interested, please check my last video here. Now in this case, just look at this. This is the PSD of the white Gaussian noise, okay, restricted within the transmission bandwidth, which is given by M0 here. That is between the minus BT by 2 to plus BT by 2. The PSD is given by M0. Okay, that is transmission within the transmission bandwidth. When it is passed through a discriminator circuit or FM demodulator, we'll get something like this. The shape of the PSD will be something like this. That is, it is actually equal to 0 at 0 frequency, and actually increases. It increases, okay, at the frequency increases. Okay, now why this happens? Why this happens? Just look at this equation. So this is the equation again for the PSD at the discriminator output. At the discriminator output within the transmission bandwidth. Okay, which is given by N0 F square by AC square. Okay. Now if F is 0, SND of F is 0. That's what I'll get over here, right? If as the F increases, the PSD of the noise actually increases as the square of the frequency. So it actually increases exponentially here, not linearly, but exponentially it actually increases. So we'll get something like this, the curve for the PSD at the FM receiver output or discriminator output. Now, after passing through a discriminator, the next circuit what we have is nothing but it is a low pass filter. Okay, the low pass filter is actually designed only between the frequency minus W to plus W. That is the message bandwidth. Okay, so we get the same representation of the PSD, or the same noise is actually passed through with the same PSD through the low pass filter. So, but it is down here. That means it is decreased, I can say. Okay, so we know the noise PSD at the low pass filter, we know it, or the noise PSD at the output of the discriminator, so that we know, right? Now just compare that with the message signal PSD, the power spectral density of the message signal, that is SM of F is nothing but it is the PSD of the message signal. This is the noise PSD at the output of the receiver. Actually we are expecting only the message component in the output, right, not the noise. Now just look at the relationship between this and this here over the different frequency range 0 to W. As the frequency increases, the noise PSD also increases. At 0 frequency, the PSD is also 0. Now, in this case, at 0 frequency, the message signal PSD, the power spectral density, is actually very high, right? That means for the low frequency signals, the impact of the noise is actually very low, and even the message signal is also having high PSD. But when I increase the frequency here, just if you go through this band from 0 to W hertz over here, as the frequency increases, the message signal PSD also decreases. It is less. Noise is more, but the message PSD is actually less over the in the range of high frequency, right? So this is the major problem actually in the FM receivers, FM transmission. So that's why we have to use a pre-emphasis circuit which is having a response of, let us say, HPE of F, okay, before the modulation, okay, then some noise will be added in the channel. After receiving the signal, okay, after demodulation of the signal, we have to pass through a circuit called as a de-emphasis, where we actually, in this case, we increased the amplitude of only the high frequency signals. In this case, we have to decrease the amplitude of the only high frequency signals, okay, and thereby we can minimize the impact or the effect of noise. Fine. Now let us discuss about the circuitry part of a pre-emphasis circuits, okay, and what is the standard the cutoff frequency is used for these pre-emphasis circuits. Now when I say pre-emphasis circuits and de-emphasis circuits, they are nothing but they are like high pass filters and low pass filters. So just look at this. So I have a pre-emphasis circuit over here, okay. This is the circuit. I have a capacitor followed by a resistor, capacitor in the parallel arm and a resistor in the series arm, okay. So this is nothing but this is a high pass filter, okay. A pre-emphasis circuit is high pass filter. So we actually select only, because the need here is to choose only the high frequency signals, right? So my high pass filter is having a response something like this, a non-ideal response, I can say over here, okay. This is the response of the high pass filter. So this high pass filter with a value of C and R2, it is designed to generate this particular frequency response. So we are passing the message signal through this high pass filter. We choose only the high frequency signals because high pass filter passes only high frequency signals, right? It actually produces maximum amplitude for high frequency signals. As the frequency increases, the capacitive reactance actually decreases and more of the signal will pass through the capacitor and resistor R. And we have to amplify only by choosing high frequency signals, not the low frequency signal. It is not necessary, okay. Then it is modulated and transmitted. Fine. Now as I told, this is a standard. Actually some standards are done in the radio broadcasting, especially in the United States in FM transmission, okay. The cutoff frequency what they choose here is around 2122 hertz. That means the frequency above 2100 hertz are taken as high frequency signals, and we have to increase the amplitude of such frequencies with respect to this particular curve. As I again told in the previous slide over here, in the definition of pre-emphasis, just look at this: the artificial boosting of high frequency audio modulating frequencies in accordance with the pre-arranged response curve. The pre-arranged response curve is this once again, yeah. So this is a pre-arranged response curve, okay. So these are all the standard frequencies they are using there, about 2122 hertz, okay. This is the 3 dB point for which my low pass filter is actually designed, okay. The value of the R and C, okay, decides this cutoff frequency of low pass filter. The cutoff frequency is 2122 22 hertz. So above this we have to increase the amplitude, okay, the output voltage for all these frequencies with respect to this particular curve up to say 30 kilohertz. Okay, that's the range actually, 20 hertz to 20 kilohertz. They have taken up to 30 kilohertz in this particular figure. Okay, so that means suppose you want to get a 2122 hertz, the time that is t equal to RC, that's what we say. Just one second, let me choose a pen here. Yeah, so the time t, okay, equal to RC, the value of the R and C decides actually the value of time constant C there. Okay, so this value is taken as RC is selected to get the value of T, which is equal to 75 microseconds. Okay, so it is designed for 75 microseconds. So how we can get that frequency, I'll show you in my next. Yeah, just to get this here. Okay, so what we have is F is equal to 1 by 2 pi RC is the formula to calculate the cutoff frequency, that is this 2122 hertz. The standard time interval taken is 75 microseconds for RC, so that's substituted here 1 by 2 pi into RC. RC is 75 microseconds. We'll get the cutoff frequency as 2122 hertz. I mean, if you go to the European countries, the radio broadcasting, FM broadcasting, okay, this frequency comes out to be around 3200 hertz roughly. That is, or you can say the time seconds, the time t is around 50 microseconds. That's what they choose as the standard. Okay, so above that particular frequency, the frequencies are considered as high frequency message signals. With respect to this particular curve, we have to increase the amplitude. So this is actually given the gain or the output given in terms of dB. At 2122, it should be increased by 3 dB. And at say some other frequencies over here, this should be the the output voltage or the gain should be that much. Okay, means we have to increase by that much amount. Fine. So this is actually called as a pre-emphasis circuit. Now coming to the de-emphasis circuit, which actually does the opposite operation of the pre-emphasis, right? So whatever that the amplitude we have increased, we have boosted the amplitude, we have to nullify it, or we have to compensate that artificial boosting of the amplitude of the high frequency message signals. Okay, so we have to use a opposite circuit, which is nothing but it is a low pass filter. Just look at this diagram again. R in the series arm, C in the parallel arm, which is nothing but it is the low pass filter. So after demodulation, it is passed through a de-emphasis circuit. Okay, at 2122, the requirement is we have to decrease the amplitude by 3 dB, right? In the pre-emphasis, we increased by 3 dB, but here we have to decrease the amplitude by 3 dB, and proportionately for higher frequency signals, we have to decrease by that particular amount. Okay, so we designed this RC filter for 2122 hertz, keeping that 75 microseconds as the time interval, 1 by 2 pi RC formula. Okay, we will get this particular response for a low pass filter. This is the typical response of a low pass filter, right? Isn't it? So we have to decrease by amplitude 3 dB over here. Okay, so this is de-emphasis circuit. Now, this is again the same formula I have shown here. Now, what is the relationship? What should be the relationship between the pre-emphasis and de-emphasis? As I told, pre-emphasis circuit is high pass filter and de-emphasis circuit is a low pass filter, which are completely opposite type of circuits, right? Now, so that means the response of the de-emphasis circuit, here, that is the low pass filter what I use in the receiver, is opposite of this response. They should have an inverse relationship. So if de-emphasis circuit is a low pass, the pre-emphasis should be a high pass. Fine. So this is the circuit what we have to use for increasing the amplitude of the high frequency message signals. Now, what is the response of the de-emphasis circuit is? Just look at this. If it is low pass filter, it has the formula for cutoff frequency, which is given by 1 by 1 plus j f by f 3 dB. This f3 dB is nothing but it is the cutoff frequency. That is fc, you can say, or whatever that notation is. 1 by 1 plus j f by fc, or 1 by 1 plus j f by f 3 dB point. The frequency at the 3 dB point. Okay, that is the cutoff frequency, nothing but. The pre-emphasis circuit, okay, should have a response of a high pass filter, which is given by 1 plus j f by f 3 dB. Okay, so they have an inverse relationship over here. Okay, that is the requirement. So this is again the both responses of pre-emphasis as well as de-emphasis circuits are shown in the same figure. Okay, 3 dB point over here. So it is plus 3 dB at 2122 and minus 3 dB at 2122. Okay, so there is a corresponding decrease in amplitude what we are going to do at the de-emphasis circuit or at the receiver. Okay, and at the high frequency, we are going to increase by around 17 dB, plus 17 dB or minus 17 dB at 15 kilohertz. That is the audio band. Okay, the highest frequency what we consider for audio band in case of FM transmission. Now, see, we have used the pre-emphasis. We have to reduce the amplitude of, we have to increase the amplitude of the message signals, high frequency message signals. Now, what is the improvement we get? Okay, we can measure this by using a term called as a improvement factor. Improvement factor will give you the amount by which the improvement, okay, in terms of the noise performance has happened by using the pre-emphasis circuit. Okay, so we know the noise power and all we have calculated in my previous video. I have shown it. The noise power without the de-emphasis circuit is actually given by this particular formula. So this formula we have derived in my last video. Okay, now so N is equal to what? The noise power 2 by 3 N naught W cube by AC square. Now noise PSD at the discriminator output, okay, that is given by this formula. Again, I have used this formula in this video also. SND of F is equal to N naught F square by AC square within the transmission bandwidth of the signal. Now, if I use pre-emphasis circuit, okay, pre-emphasis and corresponding de-emphasis in the receiver, what will be the PSD? The PSD is nothing but, okay, this signal is passed through, okay, before passing through the de-emphasis, this was the PSD of the discriminator output, right? At the output of the discriminator, this is the PSD what I have. If I pass this signal, which is having a noise PSD equal to N naught F square by AC square through a de-emphasis circuit in the receiver, I can write something like this, right? That is SND of F multiplied by square magnitude of the de-emphasis circuit response. Okay, if I substitute SND of F, it is N naught F square by AC square multiplied by square magnitude of SDE of F whole square within the transmission bandwidth of the signal. Okay, a corresponding the average output noise power. Suppose I calculate the noise power using this PSD after passing through the de-emphasis circuit. How to do that? We can take a area under the curve of this particular PSD, right, or integration of this particular term, okay, over the interval of minus W to plus W after passing through the de-emphasis circuit, which is a low pass filter basically, right, designed designed to allow only the message components. So just take the integration of this particular component. So I'll get something like this. Okay, now the improvement factor, that is improvement factor, is nothing but the ratio of the noise power without de-emphasis circuit, that is this one, okay, divided by the noise power with the de-emphasis circuit. That is, take the ratio of this to this particular term. That's all. So I'll get a noise improvement factor something like this. That is I equal to 2W cube by 3 integral minus W to plus W the limits F square magnitude of the response of the de-emphasis circuit. So I have taken the ratio of this to this. So I'll get this particular equation. So this is called improvement factor. Okay. So usually there is a big or large improvement in terms of the ratio. Okay. Now, if I substitute, see in this equation, I have HD of F, and I know what is the equation for HD of F. I'll substitute that in this equation. I'll modify the equation for the improvement factor. This is the response. Okay, I'll substitute that in the improvement factor equation. So I'll get something like this. Okay, 2W cube by 3 integral F square dF by 1 plus F by F naught whole square. I substituted this particular term over here. Okay, so I have to take an integration of this term, isn't it? So what I'll do is I'll take this F square by 1 plus F by F naught square as x square by 1 plus x square. Somehow I convert it. So you just use the mathematical techniques, okay, and solve this. Okay, x square by 1 plus x square is nothing but it is integration of x square by 1 plus x square is nothing but it is x minus tan inverse of x. Okay, so just search it in the Google, you'll get the solution to this particular problem. So after solving this, what we get is this particular formula for the improvement factor, that is W by F naught cube by 3 W by F naught minus tan inverse of W by N naught. So this is the formula to calculate the improvement factor in terms of W and F naught. Okay, so this is or F naught is nothing but in this case is a cutoff frequency. Again, a cutoff frequency of de-emphasis circuit which is equal to 2122 in America. okay, broadcasting, FM broadcasting, and it is equal to around 3100 to 3200 hertz around. You just calculate for 50 microseconds. That will be the cutoff frequency, if not for this. Okay, so just to summarize the pre-emphasis de-emphasis circuits, the necessity is the problem with high frequency message signals in FM transmission, because the noise PST is higher, message PST is lower. So there is a more impact of noise on the message signals. So to avoid this problem, before modulation, we have to increase the amplitude of the message signals. Correspondingly, we have to decrease the amplitude in the receiver by using de-emphasis circuit. Okay. So now, just yeah. So thank you for watching this video.